Good morning, everybody. Good morning. All right. Well, let's get rolling because that's the kind of day that we got. We are going to be covering one of the most important parts of human homeostasis. I kind of alluded to this since the very beginning of the semester, but the body cares about two things above and beyond pretty much all other homeostasis, plus or minus. It's not an exact science. It's just more like this is crazy critical in human body function. One of them was blood pressure, right? Blood pressure controls so many things. It controls everything from renal function to respiratory function to how much blood's getting to the brain. I mean, it's literally it's our life support. It's our transport system. It allows everything to get to where it needs to go. So the other one is pH. Okay, and pH is one that students tend to have a little bit of this misconception of acid versus acidity, and we'll get to the bottom of that today. I referred to that earlier this semester, but I haven't actually re-taught you that AMP1 stuff. So let's go ahead and get into that. Let's start talking about what is an acid and what is a base. Earlier this semester, I asked this question, what is an acid? And we ended up with a whole bunch of different answers. But ultimately, an acid is just a proton donor. What does that mean, proton donor? Well, remember protons, electrons, neutrons. Protons have to do with a positive charge. A proton donor is any chemical that will release a hydrogen in water. That's what a proton donor means. Octet rule, yes and no. Octet rule has to do with how the whole entire chemical is set up and how each part and each element has to follow the octet rule, but hydrogen doesn't have to follow the octet rule. Hydrogen and helium, they're, very first row on that periodic table. They don't follow an octet rule. They only have 2 electrons in their outer valence shell. So what's going on here? We need to remember one thing. I think this is it's an odd little side note that I think helps students learn what's going on with dissociation and different ions and stuff like that. But we need to remember chemical bonds. We need to remember ionic bonds, covalent bonds, which we referred to earlier this semester. But ionic bonds are the ones that I think are important for you guys to remember here. So if we're reviewing what's going on with acidity and acids, we need to be thinking of ionic bonds. And if you'll recall, definition-wise, ionic bonds are the attraction of opposite charges. Yes, no, maybe so? For instance, if we had sodium and we had chloride, we have one element that has already donated an electron, and we have one element that has already gained an electron. This is going to be following that octet rule. Then these two guys right here are going to be attracted to each other. They are now magnets, right? They now have these magnetic draws to one another. And as long as they're not in water, sodium will bind to chloride. But water is crazy cool because it's got this big oxygen and it's got these 2 little Mickey Mouse ear hydrogens. And this oxygen is extremely electronegative, which draws the electrons from the hydrogen into the orbit of that oxygen. Well, it doesn't actually go into the orbit. It just hangs out closer to the oxygen than it does to the hydrogens. So this is called a dipole. You recall me going through this earlier this semester, right? And when we were talking about polar versus nonpolar. So this oxygen side of water molecule tends to be more negatively charged, and the hydrogens tend to be more positively charged. So now when I take sodium chloride, salt, and I put it into water, the sodium is going to be attracted to the oxygen side, and the chloride gets attracted to that hydrogen side. It rips this salt particle apart. Water and the properties, the polarity of water rips this molecule apart because the sodium's more attracted to the oxygen than it is the chloride. And the chloride's more attracted to the hydrogen than it is the sodium. Does this make sense? This is called dissociation. And I hope that helped a few people that didn't understand dissociation. Dissociation is not the same thing as dissolve. Dissolve now, you take a big molecule like C6H12O6, right? This is a monosaccharide like glucose. This is also fructose, galactose. They all have this exact same chemical structure. All of these molecules are bound together by covalent bonds. There's not a single ionic bond in this. So if I put this into water, will it get ripped apart? No, absolutely not. Does that make sense? This will dissolve in water because it's charged, but this does not dissociate in water. So all things that dissociate will dissociate, then dissolve. All things that can dissolve, well, not all things that can dissolve will dissociate. It just depends on whether or not it's held together by a covalent bond or an ionic bond. So let's look at this one, HCO3 minus. I'm bicarb, right? We know this is bicarb. This is bicarbonate. Yes, no, maybe so? Bicarb is not ionic. It's an ion. And this is something that's tricky for students. This is an ion. Just like chloride is an ion. This is a whole entire ion right here. So that means that the hydrogen, the carbon, and these three oxygens are all bound together by covalent bonds. If I put bicarbonate into this water, is it going to rip bicarb apart? Yes or no? No, I'm going to have bicarb in water. It's going to dissolve in that water. Does that make sense? Now, what if I have H2CO3? And this is carbonic acid. Acids donate a proton. How can they possibly donate a proton? Because you have in this molecule one hydrogen that is ionically bound to a bicarb ion. Does that make sense? So now when I put this molecule into water, since one hydrogen has an ionic bond, it's going to dissociate. And since bicarb is all covalently bound together, it's one ion, it's going to dissociate. And now I've released hydrogens into solution. Does that make sense? I call it free the hydrogens. Just like free the whales, right? Unleash the Kraken, exactly. Unleash the Kraken. Yeah, bicarb's an, yeah, that's what I've been saying. Bicarb is an ion. Bicarb is an ion, but it's bound together by covalent bonds. An ion does not need to be all bound together by ionic bonds. That's not how it works. An ion is a charged particle. Any particle that's charged is called an ion, even if it's a small molecule that's bound together by covalent bonds. That's the tricky part. Students miss this all the time. Is everybody with me? I hope that helped somebody, anybody, one person. If that helps one person understand this, then I'm overjoyed. Because now how we define an acid is a molecule that's a proton donor. But what does that mean? It's a molecule that can release a hydrogen into solution. Any molecule that has a hydrogen that has an ionic bond somewhere can release this hydrogen when placed in water because it will dissociate. So all acids have a dissociation. Right? They're all going to dissociate a hydrogen. Does that make sense? When placed in water. And what this actually does is free the hydrogen. That's what an acid is. So what's the difference between an acid and acidity? Students get this wrong all the time. It's a pretty simple idea once you understand that an acid is a molecule that will dissociate a hydrogen when placed in water, but it doesn't mean that that acid has dissociated the hydrogen yet. This is the acid. This is the acid. Yeah, but Tariq, what does that mean? This is the acid. What is acidity? Acidity is the water. Okay, acidity is what's going on in the solution. We're not talking about the molecule. We're talking about the solution here. Does that make sense? This is all about the solution. And it's how many hydrogens are in the solution. That's acidity. When you place an acid in solution, it will release a hydrogen, which now makes that solution acidic. An acid and acidity are not the same thing. Is everybody with me? The opposite would hold true for a base. A base is actually something that dissociates an OH group. It's a bit of a pain in the patella if you had to learn it like that, but that's literally what a base does, is it's going to release an OH minus. But guess what an OH minus is going to be picking up? That hydrogen, and it becomes water. Now it becomes H2O. Does that make sense? So we can kind of bypass that whole OH craziness, right? We don't want to have to deal with hydroxyl groups and all that sort of stuff. So we can end up defining a base as something that will bind a hydrogen. It's going to take that hydrogen out of solution. Does that make sense? And so now when we're talking about the solution itself, that's when we're referring to alkalinity. Alkalinity. Okay, an alkaline solution is one where there are very few hydrogens. This is still referring to how many hydrogens are in solution. It's not changing anything. Acidity is just telling us there's lots of hydrogens. Alkalinity is telling us that there are very few. Yes, no, maybe so? Is everybody understanding the difference between an acid, a base, acidity, and alkalinity a little bit better? Was this extremely helpful for anybody? I hope so. You guys can be honest. Great question, Andy. What makes a buffer? In order to answer that, we're going to have a slide on this too, but what makes a buffer? In order to answer that, you just got to understand what a buffer even is. A buffer has to do with the acidity and alkalinity. So let's go to that real quick, and then we'll come back to a buffer. Is that fair? Helps with homeostasis, yes and no. There's a lot of places in your body where we need to have a pH of, well, not a lot of places, but there are a few places in your body where you need to have a pH of 1. So we don't want to homeostatically go back to 7 or anything along those lines. But yeah, actually, Tariq, actually, I'm going to take back what I said. I'm going to go exactly with you. It does have to do with homeostasis, because wherever we are in the body, we're going to have the exact buffers to help us with that pH. Okay, let's go here. Base, alkalinity, acid versus acidity. All right, this is all related to this acidity and alkalinity. These are solution, and these are related to pH. pH is referring to what's happening in the solution. Okay? This is not referring to acids, and it's not referring to bases. That's not how this works. This is all referring to what's going on in the solution. So pH is referring to acidity versus alkalinity. Yes, no, maybe so? P in math, guys, you guys will, I'm just doing this to help you understand this a little bit better. P has to do with the log. It's a log value. Anybody remember that from like high school? Not what a log even is, but do you remember pressing that log button on your calculator like over and over? I don't know what a log, I'm just gonna press that button. That's what the P stands for. And that capital H stands for the concentration of hydrogens in that solution. It's the concentration of hydrogens. So this is a log referring to hydrogens. But here's the deal. P is actually not a log of the solution. It gets a little trickier than that. It's an inverse log. Dr. H, what are you doing to us? Don't worry, I got your backs. I promise this isn't going to be as complicated as it even remotely seemed in A&P1 or wherever else you've learned this. Because you guys remember scientific notations? 1 times 10 to the 1, 1 times 10 to the 2, 1 times 10 to the 7, whatever it is, right? Where now all we do is we take 1 times 10 to the 1, 1 times 10 to the, what did I write here? 2, and we just add that many zeros. Yes, no, maybe so? One second, sorry. Anyways, sorry, back to this. I got distracted for a second. So 1 times 10 to the 1 would be equal to 10. 1 times 10 to the 2 would be equal to 100. You're just going to be adding that many zeros to that system. And then 1 times 10 to the 7. What's bigger number? Yes, no, maybe so? That's all a log is. This literally is written as log 1. This would be written as log 2, and this is written as log 7. That's all that is. So when we're dealing with a p, it's an inverse log. So p1 would be 1 times 10, and we're inversing this. How do we inverse a power? Easy. Just put a negative sign right in front. So this would be 1 times 10 to the minus 1 if it was a p1. So if we're dealing with a p of 1, now we're dealing with 1 times 10 to the minus 1. If we're dealing with a p of 7, we're dealing with 1 times 10 to the minus 7. If we're dealing to p14, it's 1 times 10 to the minus 14. Does everybody understand just the basic text there? Now, just let's do this real quick, and we don't have to go crazy on this, but 1 times 10 to the minus 1, right? All we're doing is we're taking that 1 with a minus 10, so we're going to take that decimal place and we're going to move it over 1, right? You guys remember how to do that? So that's going to be 0.1. Next one, 1 times 10 to the minus 7. Now we're going 1, 2, 1, 2. Goodness gracious. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6, 7. Okay. Whew. Yeah, thank you. And then the next one's going to be 1, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0. I don't know, and I think another 0. Oh my gosh, it's just such a tiny number. Which one of these is the biggest number? A p of 1 or a p of 14? I mean, this should be obvious to you. Now, throw in an H, where the H is the concentration of free hydrogens in solution. So a pH of 1 has a concentration of hydrogens of 0.1, whereas a pH of 14 has a concentration of hydrogens of 0.000000000000001. Do you guys see how few hydrogens are in a pH of 14 now? And how many hydrogens are in a pH of 1 relative to one another? And that's all the pH scale is. You guys feel a little bit more comfortable with the pH scale? That's all it is. One big problem from here, problem, I don't know if it's a problem, but you've got to think about this, because in the real world, we talk about acidity and we talk about acids. And sometimes we try to use them interchangeably, but that's very confusing, because if I have a acidity or a pH of 4 relative to a pH of 7, is that increase, decrease, no change? Work with me. I know it's simple, but if I have a pH of 4 to 7, is that increase, decrease, no change? I'm talking about pH here, so I'm talking about the acidity. Decrease. You had it right the first time, Tariq. Don't double whatever, second guess yourself, man. You had it right. Right? 4 is lower than 7, so there is a lower acidity. Yes, no, maybe so? But how many acids were required to make that lower acidity? Increase, decrease, no change. Did we need more acid in the system or less acid? So if on a test or a homework problem I'm asking about the number of acids, you've got to be able to take your brain and be able to invert that for pH, because I could be asking for the number of acids or I could be asking for the pH. Okay? Read the words carefully and make sure you're discerning between an acid and acidity. because it's going to completely give you the opposite increase, decrease, no change answer. Yes, no, maybe so? You guys rock. Thank you. All right, so back to the lecture. Got a pH scale. Now you guys are a little bit more aware of where these values are even coming from. It's an inverse log scale. I mean, we're talking, you know, huge changes, huge fold changes in the number of hydrogens in solution. The human body, however, doesn't use this full range. Thank goodness. The human body just uses a small portion of the range. All right, a value you guys must know, you 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 must know. You get the point. You got to know that this average homeostatic range of blood pH, this is your blood pH. This is what's important for homeostasis, is your blood pH, is 7.35 to 7.45. Homeostasis for blood pH is 7.35 to 7.45. That's your range. Venous blood tends to hang out at more about 7.35. Arterial blood tends to hang out more around 7.45. Venous blood has more carbon dioxide, so it's more acidic. We'll come back to that. Nonetheless, this is probably one of my favorite slides of the entire semester. Don't know why. I just love these little smiley, frowny faces. It's just great. Normal pH, happy, happy. Now, we start deviating from normal pH. Very small value, 7.35. By the way, what's neutral? What value is neutral in a pH scale? What about 7.01? What is that? I think we talked about this earlier this semester. Now I'm having a little bit of a memory. Good, right? Exactly 7 is neutral, and that's it. So when I'm looking at the range, the normal healthy range, what am I? Am I acidic? Am I basic? 7.35 to 7.45. 7.35 to 7.45. That's going to be more basic, right? Anything less than 7 is acidic. Go back to the scale here. Anything less than 7 is acidic. Anything greater than 7 would be alkaline. Basic. Yes, no, maybe so? So the normal range of body pH is 7.35 to 7.45. So the normal range is slightly alkaline. It's slightly basic. Yes, no, maybe so? This will be important. Why would we need to have a blood that's slightly basic all the time? What do you guys think is more common? Fighting against acids or fighting against bases? Yeah, we're fighting against acids all the time. And again, Andy kind of already hit that nail on the head, but what is the primary, yeah, there we go. What is the primary molecule in the body that's getting turned into acid? What are we constantly fighting against? CO2. Cool. So normal pH is 7.35 to 7.45. Let's look at this though. 7.35. Let's say we have a patient that's 7.3. They aren't happy. Their body is going to be fighting hard to get back to 7.35 to 7.45. Super hard. It's going to make them very sick. And if it happens long term, they are going to have some issues. This is called acidosis. Does this patient have an acidic blood if they're between 7 to 7.35? No. But is it more acidic relative to homeostasis? Yes. And that's why it's called acidosis. Okay, what disorder occurs when the blood pH is less than 7.35. No, Heather, drinking alkaline water will actually potentially cause liver failure. It's been linked to lots and lots of liver failure. Don't do it. Okay, acidosis. Acidosis. Versus if we're greater than 7.45, we're more alkaline than homeostasis, so we call it alkalosis. And the range is actually pretty darn narrow. 7 to 7.35, we are very, very sick. And if you get less than 7 for any period of time, you have a dead patient. Anything greater than 7.8, your patient's probably going to die. Now, got a funny story that comes around with this. I don't come back to some of our later lecture too, but I have a previous student who still texts me and lets me know what's going on. I love it. Yeah, the student was working at an ER while taking my class, and I gave this lecture, and I think I was a little bit too strict on this. I'm like, man, if your patient gets less than 7, they be dead, right? That's what I literally used to say. They be dead. But he texted me like, yo, Dr. H, I had a patient come in, blood pH 6.8. They didn't die. Okay, absolutely. So what's going to happen, especially in cardiac arrest patients? Cardiac arrest, heart attack, their heart stops. Their heart stops. What's going to start happening to the CO concentration? Building up inside of the blood. Increase, decrease, no change. No, those cells are still metabolizing. So yeah, Veronica, Becca, the cells are still metabolizing, right? So they're still using what O2 is left in the system, and they're still making CO2, even if everything else stops. So CO2 levels start to go through the roof, and carbon dioxide, of course, gets converted into carbonic acid, and boom, now all of a sudden we have an extremely acidic environment. This is always going to occur, if your patient dies, technically. They're going to get into a state of acidosis. But what are those ERs and the EMTs even? What are they supposed to be doing with these patients that they know are going into acidosis? They're putting them on a bicarb drip. Yes, no, maybe so? If anybody's ever worked in a hospital, they know about these bicarb drips. They throw them into these patients that have acidosis. Bicarbs, of course, are going to help neutralize this system. We're going to see how the body uses those bicarbs to help maintain homeostasis. But yeah, I mean, that's what you do with these patients. And they put him on a bicarb drip. They got his heart started back up again, and he survived. But they had to put him on that bicarb drip in order to get rid of the 6.8, or he would have died, regardless of whether his heart got started back up or not. The funny things that most people don't think about, the bicarb's almost more important than restarting that heart. Why? Because of how important hydrogens are, and because of how important potassium is. What potassium? What are you talking about, Dr. H? The hell's potassium got to do with anything? Let's talk about those hydrogens as denaturers first. Remember, our stomach uses hydrogens to digest proteins. So now think of those same hydrogens in our bloodstream denaturing proteins. And we can't forget that enzymes are proteins. All enzymes in the human body are proteins. So if the hydrogen levels get too high, if pH drops too low, then this will end up impacting enzyme activity. It's going to denature those enzymes. Yes, no, maybe so? And what do enzymes do? They catalyze reactions. So all chemical reactions in the human body, all chemical, not just carbonic anhydrase, all chemical reactions are going to be affected. This is going to cause severe CNS depression if we have acidosis. The part of the central nervous system that we care about the most when it comes to CNS depression are the respiratory groups. Because if the respiratory groups get depressed, and we're not talking about depression like I'm sad, depression literally means slower brain activity. We've just used that term for a disorder of people that tend to go into a state of depression. But that just means that their brain has less excitability. That's all that it means. So CNS depression, think of those respiratory groups getting depressed. What's going to happen to your patient if they go into acidosis that's too severe for too long? What's the simplest way you guys can define? What's going to happen? Die. I like it, but how? That is the simplest. You're right. Become a little. Let's go a little bit more detail. Respiratory groups, guys. Respiratory groups just got depressed. What's going to happen? Respiratory system helps you breathe. Yeah. Now all of a sudden you stop breathing. Your diaphragm stops contracting. You guys see what I'm saying? What do you now know about, yeah, well, we don't need to get too much into that, but like drug overdoses typically cause acidosis, metabolic acidosis. Shuts down that brain, shuts down the respiratory group, alcohol poisoning, right? All that sorts of stuff. Can you call enzymes hydrogenases? Some hydrogenases, well, all hydrogenases are enzymes. Not all enzymes are hydrogenases. How about that for an answer? Alkalosis. Now alkalosis is the opposite. We have too many OHs, and that's going to end up causing that nervous system to become overly excitable. We start getting seizures, and then they drop into a coma and then die. So it's no bueno. What about these potassiums, Dr. H? What's that got to do with anything? You guys remember this quick table that we pounded out yesterday? If I have acidosis, what did we say the body's going to try to do with all those excess hydrogens? Reabsorb more or secrete them? We already have too many hydrogens. What's the body going to want to do? Secrete them or reabsorb more? So what type of intercalated cells are going to be functioning in this process? And what else do type A intercalated cells, what else are they doing? As long as these intercalated cells, type A intercalated cells, are functioning, they are reabsorbing potassium. So what's starting to happen to the blood potassium levels? Increase, decrease, no change. The more hydrogens we have in the system, the less hydrogens we secrete. The more hydrogens are in our blood, and we start getting hyperkalemia. As we start to have alkalosis, we don't have enough hydrogens. Which type of intercalated cell is going to come into play if we don't have enough hydrogens? Type B. We're going to be reabsorbing more hydrogens, getting rid of some bicarb, but at the same time, there's just, this concomitant secretion of potassium. And so that blood's going to start to become hypokalemic. Does that make sense? Pretty big deal. Now, carbonic acid is not the only source of acid. It is the #1 source of acid by a long shot, though. But there are other acids that you are producing all the time, from breaking down inorganic acids to breaking down organic acids. Okay, both of these are going to cause excess acids in your body. So inorganic acids, you're going to end up with excess sulfuric acid and phosphoric acids, versus organic acids. These are the ones that you guys think about the most. So, triglycerides and proteins. This is where we're going to end up getting more fatty acids and amino acids, lactic acid from exercise, This is actually caused by a state of fermentation. Glycolysis goes crazy in our cells. And then ketonic acids, which I've mentioned a few times this semester, keto acids, like acetone. Anybody ever used fingernail polish remover? Smelt it? I'm guessing the answer is yes for like everybody. Your body produces that. That's a ketone. Makes you start to think about those ketogenic diets, huh? Would you ever drink a bottle of acetone? I hope the answer is no. But your body's producing that. It's an organic acid. Now, here's the deal. Here's the funny deal is what have we always, oh gosh, I'm not going to get into this in too much detail. I just want to make sure you guys are educated on this. I bash on keto acids all the time. I think I'm just done with the whole fad, the ketogenic acid fad, and I need to stop being so biased about it. Because there are benefits to the ketogenic diet as well. The primary benefit is, what have we been taught probably since the day we started biology? What energy source does your brain require to function? What energy source? Yeah, we've been taught it's glucose, glucose, and more glucose, right? The only way your brain can function is if it has glucose. That's not true. The brain can also function on keto acids. If there are no glucoses available, keto acids will do the same job. And that's one of the things that people with like brain cancer, what you want to do is starve those cancer cells, and those cancer cells require glucose for their function, whereas the rest of the neurons in your brain can use ketonic acids. Boom, there we go. We put that patient on a keto diet, and it will help with the regression of that cancer because that cancer doesn't have tons of glucose for its function anymore. So there are things that we can do to utilize the same, this process. Some say, I've read a lot about that. They're smarter and all that sort of stuff. I think Elon Musk is basically on I don't know. He's on some sort of weird diet. He's on some sort of weird everything. Okay. But that's another source of acid. So if we have somebody that is like literally on a ketogenic diet, they're going to have a lot of keto acids in their bloodstream. So their bloodstream will be more acidic than somebody else's. Does that make sense? Somebody that's exercising has a boost in lactic. Somebody that exercises a ton is going to be breaking down triglycerides. They're going to be tearing their muscles, breaking down muscles, and having massive boosts in lactic acid, and probably even having more keto acids because you're breaking down those fats for energy. So somebody that exercises extensively is likely going to have acidic blood as well. So these are just kind of things to think about. Now, let's get back to that buffer question. What is a buffer? Too many people think that a buffer is bicarb. That's true and false. A buffer is defined as anything that is going to help to minimize drastic changes in pH. I know I just read a slide and I hate doing that, but that's such a clean definition of what a buffer is. A buffer is something that will minimize drastic changes in pH. If you don't have a buffer, this was part of your AMP1 lab, but I don't know what you guys did with online courses. But in AMP1, you just take water and you start adding hydrochloric acid to it. How fast is that acidity going to drop? How fast is that pH going to drop if you just take hydrochloric acid and put it into a non-buffered water? It's going to drop within just a couple of drops of hydrochloric acid. It's going to go from 7 down to 3 with just like 2 or 3 drops of hydrochloric acid. That's all it takes. It's an immediate. Whereas when you put a buffer in there, you're adding hydrochloric acid, it might take 100 drops to get to that same level that it took without the buffer. Does that make sense? That pH is still going to drop because you're still adding acid to the system. It's just minimizing those changes. It doesn't actually neutralize. A lot of people like to use the word equilibrium or neutralization. I'll even use that word sometimes, but it's not exactly right. The buffers are always going to minimize those drastic changes in pH. So what if we have a pH of, I don't know, 7.7? We got a really sick patient. We still need buffers to help with this system. What buffer are we going to be using here? Yeah, we still need more hydrogens. You got it. So the way this works, I'm actually going to utilize a little bit of this space over here because it's a big ass sketch pad with almost nothing on it. The way these buffers are going to work is that if we want our blood to be at 7.35 to 7.45, and it starts getting greater than 7.45, okay? It's getting over here to 7.5, 7.6, 7.7. What do we want to do if it's greater than 7.45? Do we want to add hydrogens to the system to drop that acidity, or do we want to add bases to that system? Do we want to bind hydrogens up? Yeah, so we're going to want to add hydrogens. And what is an easy source of adding hydrogens in the human body? We want to add hydrogens to this system. Not hydrochloric acid, because that's only occurring in the stomach, and we don't want hydrochloric acid in our bloodstream because it's so powerful. Does that make sense? You're not wrong. That is an acid in our body, so I'm glad that you went and talked about it. But what is the most readily available source of acid in the human body? By a long shot. CO2 is the molecule. Good, good, good. But what is the acid that it makes? You got a couple people that answered it up above, so you guys can, yep. So now we're talking about carbonic acid. So if it gets greater than this value, what is the body going to do? It's going to take H2CO3 and it's going to release a hydrogen. Release a hydrogen to try to bring this back down to 7.35 to 7.45. Therefore, this is called a buffer. This is a weak base, or sorry, this is a weak acid buffer. Carbonic acid is a weak acid buffer. It can release hydrogens into solution when we need it to. It also is going to release hydrogens into solutions when we don't need it to sometimes, but that's a whole nother story. So now what would happen if we got less than 7.35? Now we are in acidosis. Do we want to release more hydrogens if we're already in acidosis? No, 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 no. We don't want to release more hydrogens. What do we want to do to those hydrogens that are in the solution? If I'm down at 7.2, I want to bind those hydrogens up now. Yes, no, maybe so? So what we need is a weak base buffer. And what is the number one weak base buffer in the human body? Now we're talking about bicarb. And that's now going to pick up that extra hydrogen, right? So now that's picking up that hydrogen. But look what we're doing here. I take bicarb, I add a hydrogen, I make carbonic acid. So I go from a weak base buffer to a weak acid buffer. And I'm just going to jump back and forth between these in the body. Pretty cool, huh? It's this really nice, smooth balance during most normal everyday activity. Does that part make sense? These aren't the only buffers in the human body, by the way. You're going to have a table in just a second that goes through the rest of them, but those are the most important buffers in the human body. Now, the last part of this, and I'm actually going to go ahead and go to this table for this idea, is that what part of our body, what system, organ system of our body controls carbonic acid? and how much carbonic acid is in the system. What molecule helps us make carbonic acid? Nope, not what organ system, Tariq. So what molecule, let's go with this, what molecule is helping us produce all carbonic acid in the body? CO2. CO2, carbonic anhydrase, is required to run the chemical reaction, but that chemical reaction can occur without carbonic acid, just not to the same degree. The answer is CO2. And what organ system of the body controls CO2? What organ system? What organ system? I love you guys, though. Now we're talking about the respiratory system. Okay? Does this make sense that this is helping to control the respiratory system? They're not helping to control, but this is controlled by the respiratory system. Respiratory system. So this respiratory system is always going to be related to CO2. Always. CO2. Always going to be related to CO2. And that's why the respiratory system controls 70% of all of your pH levels. Yes, Tariq. Does that make sense to everybody? Because we can get rid of CO2, we can retain CO2, so forth, so on. Cool. 30% is controlled by the kidneys. And big reason why it's controlled by the kidneys is because bicarb. How does the body determine how much bicarb is in the system? We've got to remember that bicarb is coming from multiple sources, from the digestive system, from the urinary system, from the respiratory system. Bicarbs are coming from a lot of different systems. Your CSF produces tons of bicarb. The body controls how much bicarb's in the system via what we talked about yesterday. We talked about it only briefly, unfortunately. We're talking about it more now. But that is under renal control. We deal with, remember what I said, like 20 pounds of bicarb is getting reabsorbed every single day. You guys kind of remember that? I wanted to make it drastic, so that it was just like this value that, I can't remember exactly what it is. It might be like 13 or 14 pounds, but it is pounds of bicarb. Pounds of bicarb that's controlled by the renal system. So when we're dealing with bicarb in the body, what we're actually talking about is renal system. Okay? Renal system is always referring to HCO3, whereas the respiratory system is referring to CO2 and carbonic acid. Next. Next is where it gets complicated. But I think I've given you the background to make this a little bit less complicated. Because next we're going to be talking about homeostasis. This is the physiology of what your body is doing every second of every day. Normal blood pH range is what? Everybody write it down in chat for me. What's the normal range? Not average, range. .35 to 7.45. We've already done this a few times, so just keep working with me. Redundancy is the key to learning. If we go into alkalosis, increase, decrease, no change, what's the body going to try to do? We'll get there, Tariq. We don't just need more hydrogens. There's a lot more we're going to have to do. But if we go into alkalosis, what's the body going to try to do to blood pH? Increase, decrease, no change. If our body goes into acidosis, what's the body going to try to do to blood pH? Increase, decrease, no change. This is called compensation. We talked about compensatory feedback loops. Negative feedback loops are basically a compensatory feedback. So when the body starts to fluctuate between these ranges, even when we're down at 7.35, we're kind of range it back up to about 7.4. We kind of want to balance it in between these all the time. We're going to have what's called compensation. There's a chronology of how the compensation in your body works. Chronology means there's a time frame for everything. There's an immediate reaction. There's a reaction that's going to be occurring over the next few seconds. And then there's a reaction that's going to be occurring over the next few minutes, days, weeks. The first response in the human body is immediate. So the very first compensatory response is immediate. We're talking right now, right? It's occurring immediate because it's a chemical reaction. The very first way that your body can compensate for changes in blood pH is using buffers. So the first compensatory mechanism is buffers. Buffers. We've already done this. Let's just do it again. If the body is in acidosis, what buffer is going to be working? If we're already in acidosis, do we want to be releasing more acids, or do we want to be binding those acids up? We're going to want to bind it. Perfect, and you guys are already there. What molecule is going to be doing its job if we go into acidosis? Even if we're down at 7.35, what molecule is trying to bind up all of those excess hydrogens? Bicarb. What about if we have alkalosis? Now, what buffer is trying to do its job? Again, these aren't the only buffers. They're just the primary buffers, and they're the only ones that I'm going to test you guys on. Okay, now we got carbonic acid. Does that make sense? And this is occurring right now in your bloodstream. Okay, every microsecond of every day, you have a buffer system that's keeping you from dying. Congratulations. The second compensatory mechanism, what if the buffers can't fix the problem right now? I want to put this into perspective. Who's ever ran up that flight of stairs? You know, you're late for class or whatever the case might be, and you run up that flight of stairs, and you're like, damn, I gotta work out more. What are you doing when you get to the top of that flight of stairs? You're huffing and puffing. You're breathing heavy. Yes, no? And the reason why is because exercise and using your muscle produces lots of acid. And your bicarb system wasn't enough to fix the problem in and of itself. So the second compensatory mechanism, it's not like you're going to start breathing hard just because you stood up from your chair. If you do, by the way, there are patients that do. We know there's some problems, right? If they start breathing harder, they get wheeled in a wheelchair, and they just stand up and walk 5 steps, and they start panting. You know there's a problem, and you know there's a problem with their acid and bases, by the way. Probably due to something like heart failure. No, Heather. Great question though, but no, no. I don't want to go too much on a tangent because we only have 20 minutes left, and I have, you know, a really powerful end of the message that I got to go here. But no is the answer. You can look a little bit of that up, or you can talk to me more about it. But that second compensatory mechanism, this is the respiratory system. Okay, so it's called respiratory compensation. This is where hyper and hypo ventilation can be very helpful, can also be problematic. But if our patient is in acidosis, then their body has too many acids. And what do we know about the respiratory reflex? If there are too many acids in the system, are we going to breathe faster or are we going to breathe slower? To get rid of those acids. Remember, we're breathing faster. Good. And what acid would we get? What molecule are we getting rid of as we breathe faster? Yeah, now we're getting rid of CO2, so now our body produces less carbonic acid. So even if the source of acid is ketonic acids, we're still going to breathe faster to get rid of CO2 to try to compensate for that. Does that make sense? If you recall, this is called pulmonary ventilation, PV, right? Pulmonary ventilation was equal to the respiratory rate times the tidal volume. So if we have acidosis, we're going to be increasing our respiratory rate and the depth of our breathing. Does that make sense? If acidosis, what's going to happen to pulmonary ventilation? It's the opposite. So now we start holding our breath a little bit more. We have slow breathing. Some form of slow breathing. Brady. Oh, man, I keep getting distracted by, you know how I had my roof redone like way long ago? They still haven't fixed my gutters, so I'm trying to get a hold of my my roofing company, be like, where are my gutters at? Anywho, yeah, so both of these are going to be impacting CO2. If I increase that pulmonary ventilation, the end result, what we're after is this is going to end up decreasing the available or partial pressure of carbon dioxide in the blood. Whereas if I decrease my pulmonary ventilation, I will end up increasing that partial pressure of carbon dioxide in the blood. So that's how it helps. Why did I write acidosis twice? Why didn't nobody catch me on that? I blame, who am I going to blame? Oh, you did? I just didn't read it. I was going to blame you too, Heather. That's not cool. Alkalosis. My bad. Sorry about that, y'all. Okay. Now, the third stage of compensation. This is the final stage of compensation. This is going to be trying to fix the problem 30 minutes, an hour, days. Depends on how long the acidosis and the alkalosis sticks around. If buffers aren't enough alone, and if your respiratory system isn't enough, what other system do we have to get rid of acids and bases, or to gain more acids and bases? Now we're dealing with renal compensation, right? Kidney function isn't immediate. I hope you guys are understanding that, right? We don't drink a gallon of water and start peeing. That's not how it works, right? We've got to go through a filtration system, and cells have to, you know, have their transporters do their due. So that's what's going on down here. And I will use, got so many colors that are just too light to use. Ah, How does renal compensation work? Well, renal compensation is all about those intercalated cells. So if we have acidosis, you guys should have the background on this already. Do we want to secrete more hydrogens or reabsorb more hydrogens if we have acidosis? Does that make sense to everybody? So which type of intercalated cells are we talking about here? So now we're talking about type A intercalated cells. And these are always going to do what? They're always going to secrete hydrogens, reabsorb bicarbs. They're also going to be reabsorbing potassium, but we'll deal with that. You know, that's part of another idea. We're not going to be dealing with potassium for our compensatory mechanisms. What about if it's alkalosis? Now we got type B intercalated cells. And we know it does the opposite because the entire cell flips. So what are we going to be doing? Well, we have alkalosis. We're too basic. Let's reabsorb some hydrogens to try to bring that back down. We're in alkalosis. We want to bring it back down to the normal range, and let's secrete some of those bicarbs. Everybody feel pretty comfortable with this list that we just wrote out? This is how the human body compensates, and this is why we see certain symptoms with certain diseases. This is why we see increased pulmonary ventilation in a heart failure patient, because they have entered acidosis. Their buffers can't keep up with the amount of acids as their body is just basically killing itself. And they just try to walk a couple of feet. And they can't get enough oxygen out to their tissue, sure, but we're not getting rid of the amount of acids that are being produced in that time. And then the patient is basically living a life in acidosis. What do we know is going to be going on with their urine? Will their urine be acidic, or will their urine be alkaline? Yeah, extremely acidic, because they're going to be stuck in type A intercalated cells, days, weeks, months. So they're always going to be secreting a high amount of hydrogens. Make sense? So let's go to the slides. The first compensatory mechanism is buffers, right? The buffer systems, the primary buffer systems are bicarbonate versus carbonic acid. And we just throw them into the system depending on whether or not we are acidic or alkalinic. There are other buffer systems. The number one buffer system is the carbonic acid bicarb buffer system, where the acid member is the carbonic acid, the base member is the bicarb. Easy, okay? But just important to think about these other ones. They do exist, like, for instance, proteins. Because remember, proteins denature when there's too much hydrogen in the system. And the only way that a protein can be denatured is if hydrogen binds to that protein. So technically, the protein is taking the hydrogen out of solution. Does that make sense? Why proteins would be a buffer? It's not necessarily good for the protein, but it is a buffer. Yes, no, maybe so. So the acid group on the proteins, the carboxyl group versus the amine group, is going to be binding up bases. So yeah, good stuff. Hemoglobin is a buffer because hemoglobin can bind hydrogens and pull them out of solution. So it's a base. Hemoglobin is a base buffer. And the last one are phosphate buffers, which are really important. I just don't have time in my semesters to talk about these monosodium and disodium phosphates. These are all occurring in the kidneys, these phosphate buffer systems. Phosphate is an ion, just like bicarb is an ion, and we can utilize these ions to bind up acids. So, yeah, good stuff. Now, second compensatory response is the respiratory system. We've kind of already covered this. Respiratory system is always CO2 related. Hopefully you guys have caught that. It's always CO2 related. I've tried to write that in everything that I've done. CO2, and then when we talked about this back here, I wrote CO2. The respiratory system is related to CO2. And CO2, of course, is related to carbonic acid. This is occurring pretty quick, right? It's going to be happening for a couple of minutes after you've had an acidosis event, like exercise. Or it could try to, this is trying to fix the problem within a couple of minutes. That's all that means. It doesn't mean that it's going to. It just means that it's going to try to. We know that if we have acidosis, both tidal volume and respiratory rate are going to increase, and we know that if we have alkalosis, both of those are going to decrease. I got a big bold thing down here, cannot fix CO2 related problems. That doesn't make sense to students yet. We're going to get there. I'm going to come back to this idea. But please highlight this, asterisk this. This was going to cause some confusion, especially as we go into the case studies, and I always test on it. So just highlight in bold, and then I'll explain it when I get to it. Right now, it just doesn't make too much sense. The renal system is going to try to compensate after everything's already happened, or potentially for long terms if you are in chronic acidosis or chronic alkalosis. But say, for instance, you exercise, the buffers and the respiratory system have fixed the problem, but you still have too many acids in your bloodstream. So now the renal system is going to try to get rid of those acids. We know that if we have acidosis, we're going to be secreting hydrogens. These are type A intercalated cells. We're going to be reabsorbing bicarbs. If we have alkalosis, we got type B intercalated cells, so we're always reabsorbing hydrogens, secreting bicarbs, and this is going to make your urine more alkaline. The presentation follows the chalk talk. Everybody cool? Any questions on that? Only a few slides left. All right, this is when poo really hits the fan. There's more than just one type of acidosis, and there's more than one type of alkalosis. The easiest way to understand that we have what's called respiratory acid-base imbalances and metabolic acid-base imbalances is to refer back to what I've been trying to get you guys to see. That is that if it's a respiratory problem, it's always going to be associated with CO2. Yes, no, maybe so? Whereas if it's a renal or any other metabolic, means any metabolism, right? This is all of the chemical reactions in the human body. So everything that's not CO2, lactic acid, ketonic acid, other organic acids like fatty acids and amino acids, inorganic acids like phosphoric acid, all of these other problems, we're going to summate into, hey, let's stop thinking about all the acid and let's start thinking about the bicarbs. Okay, that's how I'm going to get you guys, I think, to understand this the best. Is that if it's a respiratory disorder, if we're going to be dealing with a respiratory acidosis or respiratory alkalosis, what we are always going to be looking at is CO2. Versus if it's anything else, that's the rest of the body, we call it metabolic because that's all inclusive. It includes everything that's going on. Well, now we're going to be looking at bicarbs. This will make more sense. Write this down, and then we're going to actually do some examples. If we have a respiratory problem, it's going to be an imbalance in the amount of CO2 in the system. If we have a metabolic problem, it's going to be an imbalance of the amount of bicarbs in the system. So, respiratory acidosis. Respiratory acidosis is going to be caused if there's too much CO2. For whatever reason, if we have too much CO2 in the system, we're going to be entering acidosis because CO2 is going to be converted into carbonic acid. Yes, no, maybe so? The easiest way to get you guys to understand respiratory acidosis is hold your breath. When you hold your breath, you enter respiratory acidosis. It's a pretty extreme level of respiratory acidosis. Can you imagine having a disease that causes you to always have that same feeling, your brain dead, like I feel like I'm suffocating all the time? Be pretty horrible. Basically feel like you're holding your breath all the time, even though you're breathing. Respiratory alkalosis. If we have anything that causes an excess loss of CO2, if you want to experience this, hyperventilate. We're getting rid of excess CO2. The primary cause of respiratory alkalosis is something like a panic attack. Anybody ever had a panic attack where they start hyperventilating uncontrollably? Those are extremely dangerous. Shush, Tariq. Hyperventilation, like if you get on a plane and you're scared of a plane or for whatever reason, those are extremely dangerous. They cause your body to go into respiratory alkalosis. Now, here's another example that I always use on the homework and the test, so I want to make sure to point it out. And because I used to be a mountaineer, right? So I love this idea of going up in elevation. What's going to happen to the amount of available oxygen in the air as you go up in elevation? Increase, decrease, no change. So what's going to happen to the amount of oxygen inside of your bloodstream? Increase, decrease, no change. And what is your body going to try to do to compensate for that? Don't think about the acid base right now. Just think about that oxygen. What's your body going to be trying to do to compensate? You breathe faster. And you breathe harder. This is called hyperventilation. So people start to hyperventilate as they're climbing a mountain. And what's going to start happening to their blood as they're hyperventilating to compensate for this thin air? Alkalosis. This is called respiratory alkalosis. This is the same thing as saying elevation sickness, altitude sickness. Make sense? Yeah, Colorado Springs, man. You ever do anything up that high, for sure. Cool. You guys on board with that respiratory alkalosis? This is what mountaineers are going through. This is actually what kills all those people at base camp at you know, they're going up Everest and all that sort of stuff. All right. Metabolic now has to do, let's think about bicarbs. We could also think about the acids, but remember, bicarbs and acids are going to be on a teeter-totter. So when acid levels are high, bicarb levels are low. And when bicarb levels are high, acid levels tend to be low. So excess acids or loss of bases. Diarrhea is very dangerous. And I tried to get you guys to see this in Unit 3. But what is being reabsorbed in the large intestines? What's ions? Ions. Yep. And what ion are we dealing with here? And water. Yeah, the water follows those ions. Sodium, sure. Potassium, chloride, calcium, those are all ions, but you guys are forgetting something that I already talked about earlier today. There's another major ion in the system. Bicarb. Bicarb is an ion. It's getting reabsorbed in the large intestines. So if we're shutting our brains out, what are we losing? We're not just losing water. We're not just losing sodium and potassium. We're also losing bicarb. And if we lose bicarb, we're losing that base buffer. And if we lose that base buffer, we enter metabolic acidosis. See how this is not a CO2 related disorder? Yes, no, maybe so? Alcohol, that causes a boost in the number of acids in the body. Diabetes causes ketoacidosis, where these patients have constant high levels of ketonic acids. They can't do anything about it because their body can't utilize glucose properly for energy, so they have to go and metabolize fatty acids, proteins, breaking them down to amino acids, and then the Krebs cycle is producing tons of ketonic acids. So diabetic patients are always going to be in a stage of metabolic acidosis. Exercise is a disease. It's one of my favorite diseases. I always love that. Yeah, exercise is a disease. After all semester, I've been talking about how good exercise is. It is so good for you, but it does cause you to go into metabolic acidosis. So you got to be aware of that, and you got to take care of your body after exercise. And then renal failure is going to cause metabolic acidosis, because if we have renal failure, we're not going to have the appropriate control over bicarbs. Metabolic alkalosis, excess bases or loss of acids. One of the number one ones that I test you guys on is vomiting and diuretics. Vomiting, you're throwing up hydrochloric acid. That had to come from somewhere. The hydrochloric acid is hydrogens that came from your body. It came from your blood. Was put into your stomach as hydrochloric acid, and then you're puking it out. So if you have a patient that has basically a chronic vomiting problem, they're so sick they're vomiting their brains out, that can start to induce metabolic alkalosis. Where things get real tricky, of course, is a patient that's coming out both ends. Because now you got something that's trying to cause metabolic acidosis and then something else that's trying to cause metabolic alkalosis. You got a real sick patient. Does that make sense? All right. Let's put this all into context. You guys are going to be working with patients in the future. Not everybody's going to be having to go through the thought process of, is my patient in acidosis or is my patient in alkalosis? But I sure hope you guys think about it. And literally, if you have a patient that walks through the door and they're hyperventilating, you shouldn't just be sitting on your laurels, right? You should be asking them pertinent history questions about why they might be hyperventilating just from walking from the patient waiting room to the patient room itself. That's my opinion. Your doctors will tell you what the hell you actually have to do. But what you guys still be dealing with are patients that are in acidosis or alkalosis. So what you will be having to do in the future is you're going to have to be taking the blood from these patients, and you're going to be monitoring for acidosis or alkalosis. So when you take the patient's blood, the first value you're going to look at is blood pH. The second value you're going to look at is the partial pressure of carbon dioxide. And the third value you're going to look at is how much bicarb is in that patient's blood. What's the normal range of pH? When do we say the normal range of blood pH is? So on this table, I'm going to be recreating here. We want to put the normal ranges for everything. Does anybody remember that normal range for the partial pressure of carbon dioxide? That's atmospheric, but we're actually talking about partial pressure of carbon dioxide in the blood. Remember, we just drew this patient's blood. Ah, now we're starting to get somewhere, right? We're talking about 1 millimeters of mercury, right? And the number I taught you guys was 40, but there's a range because the body's not always at an average. And the range for the normal values of partial pressure carbon dioxide is 35 to 45 millimeters of mercury. Okay, so we're going to know this number. You guys must know this number. You guys must know that range. Bicarb is a new value. You've never learned this before. It's 22 to 26. It's called milliequivalents per liter. Don't overthink milliequivalents. M, capital E, lowercase q. Milliequivalents is the same thing as saying a weight. So it's just like saying, like, you know, grams over liters. So it's just a, I don't know why they got to change things on us, but they do. All right, so now what I want you guys to do is, I'm not going to write what's on the table that's in the lecture. That's just going to, you know, I think that's just confusing to most people. What I do want you guys to do is, let's say we got patient 1, well, whoever this patient might be, patient 1. And let's say that this patient has a blood pH of 7.2. What disorder do you know this patient has right off the bat? Acidosis or alkalosis? What do you know they have? End of story. Don't mess around with this. Stop overthinking this. This is acidosis. You know this patient has acidosis. Write that down. And don't ever second guess yourself. It's as simple as that. Acidosis is a blood value that's less than normal. Why am I telling you guys this? You'll see. Now, let's look at patient 1's partial pressure of carbon dioxide. And let's say that this partial pressure of carbon dioxide is 57 millimeters of mercury. So is this a dumb question? I know. Is this too high or too low? We'll get there, Tariq. You're not wrong. Is this too high or too low? Step by step, because I want to make sure everybody's on board with this. So now if I have too high of carbon dioxide, then I'm making too much carbonic acid. So is this going to be indicative of acidosis or alkalosis? Good. The partial pressure of carbon dioxide might be high in your patient, and if it is, we're going to be thinking of acidosis. This isn't the end of the story yet. We're going to be thinking of acidosis because that partial pressure carbon dioxide is too high, so that patient's making too many acids, potentially too many. You'll see what I mean in just a second. Last but not least, let's look at these bicarb values. Okay. Remember, bicarb is a buffer, right? So in this particular patient, let's go ahead and throw out, I don't know, 34 milliequivalents per liter. Bicarb levels in this patient, are they too high or too low? Too high. And if my bicarb levels are too high, what would I be thinking of? Acidosis or alkalosis? Don't think about anything else that we've done so far. That's not the point. Yeah, exactly. If I have too many bicarbs, I might think this is alkalosis. These are actually indicative of real values you'd get from one patient. The way we use these values is as follows. What do you know this patient has? Acidosis. Which one of these two value matches? Partial pressure of carbon dioxide or bicarb levels? Which one of them matches? And if it's a CO2 match, what type of disorder will this patient have? Respiratory or metabolic? Drop the mic. Does that make sense? And we'll come back to alkalosis. Why is this alkalytic? So weird. But if it matches, which this does, now we got respiratory acidosis. Why is it respiratory? Acidosis. Why is it respiratory? Because it's a PCO2 related disorder. Yes, no, maybe so? So what's going on with the bicarb? What's going on with this patient? Who wants to answer that? What's going on with that patient? Yes, Andy, beautiful. Woohoo, you guys got it. Ash, Veronica, anybody else that was thinking that, what do we know is that if the body is in acidosis, it's going to have buffers trying to compensate. So the respiratory system is going to try to compensate, and the renal system is going to be compensating. What is going to be happening with this renal compensation? If I'm in acidosis, what kind of cells are doing their thing? Type A or type B? And type A are always going to be secreting hydrogens. I'm in acidosis. I'm trying to get rid of those hydrogens. And what am I reabsorbing a shit ton of? I'm secreting the hydrogens and I'm reabsorbing the... And don't we see that right here? This patient's bicarb levels are higher than normal because those type B or the type A intercalated cells are reabsorbing those bicarbs. Does that make sense? We're trying to compensate for the acidosis. Love you guys. Great job. What about if I had 7 point, I don't know, let's make this patient really sick. 1. What do you know this patient has? No matter what. No if and or buts. Don't mess around with it. You know this patient has acidosis. Now, what if the partial pressure of carbon dioxide is 22? Well, that's going to indicate alkalosis. Okay. So we're going to write that down. We'll say acid, and we'll say alk. I don't know. Just trying to put something out there. I'm running out of time. I'm out of time, to be honest, but you guys are forgiving, I hope. Now, last but not least, let's go ahead and say these levels are low. So this patient's real sick. So we'll go 12 milliequivalents. What am I doing here? 12 milliequivalents per liter. So if I have a really low amount of bicarb, what am I thinking? Acidosis or alkalosis? And now this matches the disorder. So does this patient have a CO2 related disorder or a bicarb related disorder? Good. And if it's a bicarb related disorder, is it respiratory acidosis or metabolic acidosis? And what's going on with the partial pressure of carbon dioxide? Why is this so low? Compensation. What is that patient doing? Hyperventilating or hypoventilating to drop that CO2 so low? Try again. Try again. Actually, don't try again. That's right. You're right. I'm right. You're right. No, you were right. I got too excited. You guys were so right. It's hyperventilation. We're breathing too fast, and that's blowing all that CO2 out of the system, and that's why it's so low. That's respiratory compensation. Yes, no, maybe so? And the last little bit that I promised that I'd come back to today, and I'm going to do it, is that in our first patient that had respiratory acidosis, are they hyperventilating? Probably. But can their hyperventilation fix the problem? If the problem is a problem of the respiratory system, can the respiratory system fix that problem? No. It's impossible. So do you guys remember this slide back here where I said highlight, bold, where the heck was it? Here. I said cannot fix CO2 related problems. The respiratory system cannot cannot fix CO2 related problems because the problem's with CO2. Can't fix something that's broken. And yes, that's when the kidneys really kick in, and these patients almost always end up in renal failure because the kidneys get overworked. So we got a respiratory disorder that causes kidney failure, and then shit, now the kidneys have failed. So what's happening to your blood pressure and your blood volume and everything's going out of wonk? Now your heart fails. It's the trifecta of organs. And now the nervous system starts to die. That's no bueno. Thank you guys for sticking around so long with me today. I really appreciate that. I have a final slide. You guys can walk through this on your own. This is what I just did, right? We just step by step, I write down the instructions on how to determine whether or not it's metabolic versus respiratory, whether it's acidosis versus alkalosis. So this is just that step by step, the same logic that I used to make this table. Okay? Now we're done. Yep. Yep, we'll do the case studies on Monday, but I will need you guys to listen to me. We are done with the renal system. We're going to be going into the respiratory system, and I'm going to write up an email for everybody. Did I just say respiratory? That's weird. Reproductive. Thank you, Ashley. Just trying to go fast because we're so far over time. I mean, I could be here all day, but you guys don't want to be here all day. We got repro that we still need to go through. And so somewhere is a repro anatomy. See this one right here? Reproductive anatomy, summarized, narrated. You guys must have watched this by Monday's class. I'm giving you guys homework, and I don't like doing that, but you know, for a summer of very little relative, very little, right? I'm not making you guys do minutia homework all the dang time because I hated it as a student. That's why I just have one homework per unit. But I am giving you guys homework. You're going to watch this narrated PowerPoint and you're going to go through the flow chart of reproductive anatomy before coming to class on Monday. Everybody, hear me? Because summer. Only 1 week left. Yep. You guys can come by campus. I get to teach face-to-face in the fall. So if anybody ever wants to meet me face-to-face, come on by Round Rock in the fall. I'll be there. Yep. Yep. So if you guys get into like the ACC nursing program or something like that, then I won't know you because all I know is a name on a page. But come on by. Tell me that you took my summer course. But that's all, that's outside of the box of what needs to happen here. So reproductive anatomy summarized, narrated. Everybody cool on, maybe not cool, but everybody understand that they need to have that watched, take note, write some flow charts before Monday's class, because I'm skipping it. I'm going straight into reproductive physiology. So that one is going to be on you. And then we'll cover it, do a drag and drop in lab. So we will cover it, but I'm not going to go through it in the same amount of detail as I normally would. It's all right there in the narrated. All right, you guys rock. Thanks for staying the extra couple minutes with me. Couple minutes. You like how I said couple minutes? You guys have a great day. Text me if you need me. Tariq, you got a question, buddy? Go for it. Anybody that has questions can always ask them.
I do, Professor. So I just want to be clear and prepare for the grand finale this weekend. So we're doing Monday and Tuesday lectures, and then Wednesday is when we take the Unit 4 exam.
Yes.
Which would be
Wednesday at night.
Thursday. I apologize. Thursday.
I think Wednesday is the 21st, right? Monday, yeah. Tuesday, Wednesday. So Wednesday, 21st is when the homework is due. Yeah, exams the 22nd. Awesome. Yep.
Basically leaving us one day to study the material we studied a day before.
Well, you won't be learning anything the day before. That's all review.
Case studies. Okay, sounds good. Perfect.
Right? Isn't that July 21st? I kind of have down as review. So we're basically just going to be reviewing not just Unit 4, but we're going to try to review this comprehensive idea that AMP is always working from day one, where you're learning about atoms, and we build those atoms, and we end up getting to where we're at now. That's kind of what that review is going to be all about. And then the 22nd, we're going to have review as well. So yeah, I hope I'm done with the reproductive physiology on Tuesday. I should be, especially if you guys, that's why I had to do the homework for reproductive anatomy.
Yes, sir. And for the final, it's due by 25th midnight, and you did mention that it's mandatory, but
Yes.
does that final replaces one of your lowest grade, or
Nope.
just...
No, I drop your lowest test grade. If that lowest test grade is the comp final, then I drop it. You still got to take it, and you still got to try. I've had plenty of students that are getting an A in the class that go in and not study, and I completely support that. Like, if you don't want to study for the comp final, if you want to test your knowledge based on what can I actually remember from the entire semester, I love it. As long as you try. You know what I mean?
Sounds good, sir. Perfect.
Yeah, because a lot of people do have a busy end of the semester. I want to make these comprehensive finals. They're going to be hard. It's going to be hard, but I want to make it something where you guys can be proud of yourself and your accomplishment through the semester. Yeah, so that's the idea behind the comprehensive. There is no comprehensive lab, so there's no way to make up a lab practical grade.
Sounds good. And just to be clear, you mentioned that there's students who would not take it because
Nope. Everybody's got to take it. It's
Okay.
mandatory to take. It's not an
Okay.
optional. If you don't take it, then I replace your lowest test grade with a 0.
Okay, sounds good. Perfect.
Yeah, it's definitely a must-have. You gotta test yourself. You have to push that knowledge bank. I know you're just trying to get some understanding of what's actually, required versus this optional idea. It is not optional. You gotta take it, and you gotta try, but you don't have to study for it. Does that make sense? The
Yes, sir.
difference?
Yes, sir. So
Right? You can test your knowledge bank.
sounds good. So you have to take it, but
Perfect, Andy.
if
Yep.
it's lower, then it gets dropped.
Exactly. I drop
Okay.
your lowest exam grade, even if that lowest exam grade is the comp. And it's very well likely, because the comprehensive final is not easy. I mean, I push you guys through the semester to get, to a level of a doctor. I mean, I'm not messing around. You guys shouldn't get a lesser education just because you're at ACC. So, yeah, ACC, man, we teach the same level or even above level of UT. I mean, I get these UT students that are like leaving my class and they're in way better shape than they ever were with University of Texas. So, yeah, man, yeah. Push you. I'm a pusher. Remember that on Mean Girls? I'm a pusher. And then, of course, she gets like arrested for drug dealing. Cool. Few of you stuck around. Are there any other questions about that? You're welcome. I try to give you guys plenty of time next week to get that done between, the exam on the 22nd and then the comp final on the 25th. I have to have your grades submitted by the 26th. So that's why I have you guys with the comp final due on the 25th, because that gives me a morning to grade them before I have to have them submitted. All right. Bye, guys. Let me know if you have any questions. Oh, Andy, yeah. What's up? Oh, no, Adriana. No, Andy, who's asking this question? Oh, here we go. I'm over here. Hi, Andy. What's up?
Yeah. I was just asking, I emailed you a Word doc version of Unit 4 homework. I didn't know if you wanted me to add it to the group me or anything to get it out to other people.
You know what? I saw that text yesterday and was super excited, and I didn't text you back, and I never even looked at my email. I will get it posted. That is so helpful. I know printing out the other versions can be a real pain in the patella. So, yes, yes, thank you, thank you, thank you. I'm going to be doing a lot of grading today, and so I will get that thing posted, and I'm going to double check all my due dates are open. Yeah, I got a few things that I need to do. So that's awesome. Thank you for reminding me of that.
Yeah, absolutely.
So helpful, because when you do that copy paste, does it lock up your computer?
No, and I just got a new laptop, so I'm like, look at how fast it
Lucky.
goes. Yeah.
Lucky. I mean, it literally locks my computer. I walk away, I come back 30 minutes later, and it's still just frozen. So yeah, I can't do it. I don't know what it is.
No, I just zoomed through it while watching like Netflix or something, like a zombie.
That's my life. Every day. All right. Cool. Thank you, Andy.